This is my solution video for the week 10 challenge problem. The problem is you've got these two shapes. One is a ring with an arc with an angle 2 theta naught removed on either side of the x-axis, and the other is a disk with the same arc removed. And the problem is to find the moments of inertia and centers of mass of both of these objects along with their 3D counterparts when you rotate them around the x-axis. So spherical shell with like a circular cap removed, and a solid sphere with a cone removed. I'm going to go ahead and start out by doing the center mass of the ring. We know the y center mass is 0 because it's symmetric that way. So really all we care about is the x center mass, which is integral x dm over integral dm. Dm here is going to be the linear mass density lambda times the small arc ds, which is going to be r d theta. So dm equals lambda r d theta. So integral dm theta is going to range from theta naught to 2 pi minus theta naught. And that is just going to be lambda times r times 2 pi minus theta naught minus theta naught. That's 2 pi minus 2 theta naught. I'm going to go ahead and pull the 2 out. And then integral x dm. X in this case is r cosine theta, because the adjacent leg of this triangle formed here with r as the hypotenuse. So I'm going to go ahead and pull the lambda and r out. It's lambda r squared, same limits. Integral of cosine is sine, so upper limit is going to be sine of 2 pi minus theta naught, which is equal to sine of negative theta naught, which is equal to negative sine of theta naught. And we're going to be subtracting sine of theta naught for the lower limit, so it's going to be negative 2 sine theta naught. Now we just have to divide this by that. The 2 lambda and one of the r's is going to cancel, so we're going to get now this answer is slightly different from the one that Dr. Viv provided in the problem description. Only reason for that is sine of pi minus theta naught is the same as sine of theta naught. If you draw an angle pi minus theta naught here, you can see they have the same y value. And then the reason mine is negative is because I chose my x-axis to be towards the left here. I chose the left to be the positive x direction, but both answers are still describing the same point. Now I'm going to center mass of the disk, which is pretty similar, just dA instead of ds. So there's going to be a dr in there. It's going to be areal mass density times r d theta, and then small dr that goes into the circle. Switching to lowercase r now because the mass is not all concentrated at the edge. So it's going to be a double integral. Theta is going to have the same limits. And r is going to go from 0 to big R. The r integral is just going to be half big R squared, and the theta integral is going to be the exact same as this theta integral here. And the 2 here is going to cancel with the half from the half r squared. Now for integral x dm, x is still r cosine theta. OR is going to be 1/3 big R cubed. And this cosine integral is the exact same as this cosine integral from up here. So we know that ends up as -2 sine theta. So 1/3 from R times -2 from the cosine is going to be -2/3 sigma capital R cubed sine theta naught. Now all we got to do is divide this by the integral dm. Sigma cancels, 2 of the r's cancel. And that's our answer. Again, this is a negative for the same reason as this one, just because of the choice of coordinate system. Now I'm going to do the center of mass of the 3D version of the ring, which is like a spherical shell with a cap removed from the top. I'm going to be using spherical polar coordinates for this, which I'll try and draw a picture. You have your normal x, y, and z axes, and you have one circle that is in the xy plane, and another circle that is in the yz plane. That angle there is phi, and that angle there is theta. So when we're finding dm in this case, it's a little bit different. There's still going to be the r d theta component, and it's going to be areal mass density because it's on the surface of a sphere. What we're going to get is dm equals sigma dA, and to find dA we're going to draw like a small sort of a square on the surface of the sphere, and this goes back towards the center, and this vertical part here is going to be r d theta. But this part is not going to be r d phi. That's because for different values of theta, if you imagine a bunch of circles going upwards from the xy plane, each circle is going to be getting smaller as the sphere goes up towards the top. And the radius of any given circle is going to be the distance from the surface of the sphere to the z-axis, and that is given by r sine theta. So I'm going to call that r prime d phi, and then z is going to be the distance from the xy plane, so that's going to be r cosine theta. So dm equals sigma dA equals sigma r squared sine theta d theta d phi. So integrating that, sigma and r don't change, so we can pull those out. Phi is going to range from 0 to 2 pi, because for every small arc in the circle, it's going to go all the way around the circle to make a sphere. And then theta is going to go from theta naught to pi, not theta naught to 2 pi minus theta naught, because we're really only doing half of this arc and letting it range the whole way around the circle. You could also do the full arc and let phi only range from 0 to pi. I'm just doing it this way because it's easier for me. Now there's no dependence on phi inside this integral, so it's just going to be integral from 0 to 2 pi d phi. That's just going to be 2 pi minus 0. So I'm going to go ahead and pull that 2 pi out. Now the integral of sine is negative cosine. Cosine of pi is -1, so negative cosine of pi is going to be +1. And then we're going to be subtracting negative cosine of theta naught, so that again, two negatives become a positive, and we get cosine of theta plus 1. Now for integral z dm. Again, the sigma and r squared, I'm going to pull those out. Phi still ranges from 0 to 2 pi. Theta still ranges from theta naught to pi. And we're going to have sine theta, cosine theta, d theta, d phi. Now still no dependence on phi, so we can pull that 2 pi out. And there's an identity that 2 sine theta cosine theta equals sine 2 theta. So I'm going to rewrite this inside part here as half sine 2 theta. And I'm going to pull that half out as well. So the 2 from the 2 pi and the half from the half sine 2 theta are going to cancel, and we get now the integral of sine is negative cosine, and then this 2 also needs to come out, and it's going to be as 1/2. So we're going to get negative half cosine 2 theta, evaluated from theta naught to pi. Now, cosine of 2 pi is 1. 1 times negative half is negative half. And then cosine 2 theta naught is just cosine 2 theta naught, so that's going to be negative half times that. And what I'm going to do is I'm going to pull the 1/2 out. This negative half is going to cancel with the minus from subtracting here. So this is actually going to be positive 1/2 cosine 2 theta minus 1/2. So it'll be 1/2 cosine 2 theta minus 1. Now there's another identity where cosine 2 theta equals 2 cosine squared theta minus 1. So I'm going to apply that here. This becomes 2 cosine squared theta minus 2, and then this 1/2 is going to cancel with both of those 2's. And we are going to get sigma pi r squared cosine squared theta naught minus 1. Now what I'm going to do when I divide this by this is I'm going to split this into cosine theta minus 1 times cosine theta plus 1. It's a difference of squares. This should be an r cubed, actually. There's an r sine theta, an r cosine theta, and an r from the r d theta. So sigma pi and 2 of the r's are going to cancel. This 2 here is not going to cancel. And these 2 terms here are going to cancel, and our center of mass is going to be r over 2 times cosine theta naught minus 1. Next, I'm going to do the same thing for the solid sphere with the cone removed, which is a pretty similar process. There was just a dr involved. So integral dm is going to be rho and our r integral is going to go from 0 to big R. Phi integral is still just going to be 2 pi. The integral in r is going to be big R cubed over 3. And the sine integral is the same as this sine integral here, so we know it's going to be cosine theta naught plus 1. So it's going to be 2/3 rho pi r cubed cosine theta naught plus 1. Then we need to do integral z dm. All integrals are going to have the same limits. This is going to be r cubed again, because we have r sine theta, r d theta, and r cosine theta from z. Then we're going to have sine theta, cosine theta again, dr d theta d phi. So this r cubed is going to go to r to the 4th over 4 when we evaluate it from 0 to big R. Phi still just going to be 2 pi. So we're going to get rho, we'll have a 4th from the r and 1 times 2, so we're going to get half rho pi r to the 4th times the integral of sine theta cosine theta, which we found before to be 1/2 cosine squared theta naught minus 1. We pull out the 1/2 when we use this identity here. So it's going to be times 1/4 cosine squared theta naught, 1/2. We're going to end up as 1/4 minus 1. So when we divide this by that, we're going to do the same trick of the difference of squares with the cosine. Three of the r's are going to cancel, pi and rho are going to cancel. This half are going to be multiply out to 1/4. And 1/4 divided by 2/3 is equal to 3/8. these cancel again. And our z center of mass is 3/8 r times cosine theta naught minus 1. Now I'm going to, we have all the centers of mass, so I'm going to switch to doing moments of inertia for all of these objects. I'm going to start with the ring again. General formula is integral r squared dm, where r is the distance from the axis of rotation, which in this case is the x-axis. So we found over here, that's just going to be the y value for the ring. We found that x was r cosine theta, so r is going to be r sine theta, r in the moment of inertia formula. So for the ring, we found that dm was lambda r d theta. I'm gonna get an r cubed. Theta is back to ranging from theta naught to 2 pi minus theta naught. And this is sine squared theta d theta. Now what I'm going to do is I'm going to rewrite sine squared theta as, I think, half 1 minus cosine 2 theta. Going to pull the half out front. Write that identity there. So equals half lambda r cubed one minus cosine theta d theta. Now this one is going to be just theta, and that's going to range from theta naught to 2 pi minus theta naught. So that's going to be the same 2 quantity pi minus theta naught term from before. And then negative cosine theta, integral of negative cosine is negative sine. So we get, oh yeah, it should be a 2 theta. So it's going to be negative half sine 2 theta. This up here is going to go from 2 pi minus theta naught to 4 pi minus 2 theta naught. That's the same as negative 2 theta naught, sine of negative 2 theta naught, which is the same as negative sine of positive 2 theta naught. But since that sine is multiplied by negative half, it's just going to be positive half sine 2 theta naught. And then down here, we're going to be subtracting negative half sine 2 theta naught. So again, those two negatives cancel, and this cosine term here ends up going to positive sine 2 theta naught. Now, this is a correct expression for moment of inertia, but I'm actually going to pull out the mass to get it in the form of a number times mr squared. So we found back here that the mass was 2 pi times r times pi minus theta naught. So this, or 2 lambda r, sorry. Lambda and one of the r's are going to cancel. So we're going to get I equals 1/2 mr squared and that is our moment of inertia. So what I'm going to do here, just to sort of verify this, is I'm going to check this for a couple different values of theta naught that already have well-defined moments of inertia. So theta naught equals 0 would just be a full ring. moment of inertia of a ring about its diameter is just half mr squared. So if we plug on theta naught equals 0, we have 2 pi plus sine of 0, which is 0, divided by 2 pi. So that makes sense. This times 1. And then for theta equals pi over 2, we're going to have pi plus sine of 2 times pi over 2. That's sine of pi, which is 0. And then this is, again, just going to cancel to be 1, which initially seems kind of weird, that it would be the same, but this half ring would actually be half the mass as well. So this mass is describing the mass, also dependent on a value of theta naught, not the mass for the full object when theta naught equals 0. So what you actually see if you graph this, if you graph theta naught versus I, when you start out, you're going to be at your expected value for the full object, and then it's actually going to go up a little bit, and then back down to the expected value when you hit pi over 2, and then down to 0 again when it goes to pi, obviously, because then you have nothing left. And the reason it goes up initially is because as you're removing parts of the object, like this part here and this part here, they are going to have the same mass, but as you remove parts that are further and further away from the axis of rotation, they are going to remove more from the moment of inertia because they're farther away, but the same amount from the mass. So you're actually going to be adding to the moment of inertia as you're decreasing from the mass. Now I'm going to do the same thing for the disk. R is still r sine theta. I'm just going to have a dr here. Now this r term is going to go to big R to the 4th over 4, and this sine squared term is exactly the same as the sine squared integral right here. So we know that it's going to end up as this term here. Or, yeah, no, half of that term there. So we're going to have a 1 over 4 here, and then when we rewrite sine squared theta as half 1 minus cosine 2 theta, it's going to be divided by 2 again. We're going to get 1/8. And this will be sigma r to the 4th Now if we pull the mass out again, we found the mass for this to be sigma r squared times pi minus theta naught. What I'm going to do is I'm actually going to multiply this by 2 and then change this from 1/8 to 1/4 when I write out the full thing, just so it's a clearer expression. Two of the r's cancel, sigma cancels. And this is the same expression from back here, so we know that it equals 1 at both theta naught equals 0 and theta naught equals pi over 2. So we know that I is going to equal 1/4 mr squared for both of those values, which is the expected value for a disk about its diameter. Now I'm going to do the 3D objects. For the hollow sphere, r, the distance from the axis of rotation, is going to be r sine theta. No, it'll be r cosine theta. No, it's sine theta. I just wrote this wrong here. I use sine theta throughout all of this, though. So, again, dm equals sigma r squared sine theta d theta d phi. So, when we do integral r squared dm, we're going to have sigma r to the fourth 0 to 2 pi theta naught to pi sine cubed theta d theta d phi. So I'm going to pull the phi out again, still no dependence on phi. And what I'm going to do is I'm going to write sine cubed as sine squared theta cosine theta, or sine squared theta sine theta, which is equal to 1 minus cosine squared theta times sine theta. And then I'm going to do a substitution for this integral of u equals cosine theta, and du is going to equal negative sine theta. So this is going to be 1 minus u squared times negative du. So that is going to be negative u minus u cubed over 3. And then subbing back in cosine as u, our whole thing is going to be 2 pi sigma r to the fourth so this should be just thetas, and that is going to be evaluated from theta naught to pi. Now cosine of pi is -1, so when we evaluate it at the upper bound, it's going to be -1 minus -1 over 3. So that's, I'll just write it. Minus, this is going to be a plus because the minus here and the minus here. Now this term is going to be -1 plus 1/3, which is -2/3 times -1 is +2/3, and this term is just going to stay as is. Now, again, this is a correct form for the moment of inertia, but I'm going to pull the mass out again just to get it in a form that looks like mr squared. So we found that the mass was 2 pi sigma r squared times cosine theta naught plus 1. 2 pi sigma to the r is going to cancel. we get I equals mr squared times 2/3 plus cosine theta naught minus cosine cubed theta naught over 3, all divided by cosine theta naught plus 1. Now again, evaluating this at 0 and pi over 2, the standard moment of inertia of a hollow sphere is 2/3. So cosine of 0 is 1, so that's 2/3, plus 1 minus 1/3, that's 4/3, divided by 1 plus 1, that's 4/3 over 2 is 2/3, so that makes sense. And then pi over 2, all the cosine terms are 0, it's just 2/3 over 1. Again, makes sense because it is half the mass when theta naught equals pi over 2. Now, for the solid sphere, pretty similar deal. There's just going to be an integral in R. Alright, this R term is going to be 1/5 R to the 5th. The phi term is still going to be 2 pi. And the theta term, we already found this integral. It's the exact same as this integral here. We know that it's going to be 2/3 plus cosine theta naught minus cosine cubed theta naught over 3. So phi equals, have a 2 here, 1 over 5 from the R. Again, going to pull the mass out same way we've been doing. We found the mass to be 2/3 rho pi r cubed times cosine theta naught plus 1. 2/5 divided by 2/3 is 3/5. Again, 3 of the r's cancel. And we have the same expression as in the whole sphere. Now again, checking this at a couple of key values, we found that this was 2/3 at both theta naught equals 0 and pi over 2. So 3/5 times 2/3. Again, that does work out to 2/5, which is the expected moment of inertia of a solid sphere. So yeah, for both theta naught equals 0 and theta naught equals pi over 2, we have the correct value because, you know, half the mass when it's half the volume. Yeah, that is, I believe, the whole solution to this problem. All the centers of mass, all the moments of inertia, they all follow this general trend where they go up from 0, then they go back down to the expected value at pi over 2, then they go down to 0 at pi. And yeah,